All right. So we saw a graphical approach for the fixed point stability. A graphical approach in the sense, a graphical approach to understand stability of fixed point. What is that? Can you tell me what is the graphical approach? Yeah, but what is that concept called? Cobweb. Cobweb diagram. Because the lines you'd see on the code, like lines, the red lines you saw, they were representing a cobweb-like structure. Fine. So therefore, graphical approach is a cobweb diagram. But mathematically, how can we understand the stability of fixed point is the question. So actually, we have to find a criteria for stability, a mathematical criteria for stability. Yeah. This is a simple yet powerful criteria which I am going to mention here. So first of all, we will divide our attention into two types. Fixed points basically can be classified into two types. One is known as the hyperbolic fixed point. Another is known as a non-hyperbolic fixed point. See what is a non-hyperbolic fixed point? What is a hyperbolic fixed point? First, we will cover what is a hyperbolic fixed point first. Okay. So a fixed point, hyperbolic fixed point. So have a fixed point. Since a fixed point is a special quantity, I will say denoted by x star. Okay. X star of a map, a fixed point x star of a map, say f, okay, is said to be hyperbolic if the modulus of the determinant, the modulus of the derivative, okay, modulus of the derivative of f at the fixed point is not equal to 1. So a fixed point x star of a map is said to be hyperbolic fixed point if the derivative of the function f evaluated at the fixed point star is not equal to 1. That means this implies that f prime of x star can be both -1 and 1. If it is -1, the modulus will be 1. If it is 1, the modulus will be 1. You are taking the absolute value. Okay. So therefore, we have to treat these two cases separately. What happens if f prime of x star equals to -1? What happens if f prime of x star equals to +1? These two cases will be dealt separately. Okay. So now you know what is a hyperbolic fixed point. If a fixed point doesn't satisfy this one, then it is a non-hyperbolic fixed point. If a fixed point doesn't satisfy this condition, then it is a non-hyperbolic fixed point. Yeah, something like this. Okay. So actually in real life situations and most of your problems you will deal in practical situations will be hyperbolic fixed points. That means the derivative won't be equal to 1 or -1. Okay. In most of the situation you will face that. Okay. So first we will consider hyperbolic fixed points. Okay. Hyperbolic fixed points. This case, yeah. So I will write a condition here when the fixed point x star is considered to be stable. Okay, through the derivative of the function. Okay. Assume, you have to assume f is a continuously differentiable function. Why? You have to assume this. We need the derivative. Because we are using the derivative in of the map, so we need f to be a it is not a differentiable function, you can't take the derivative. It doesn't exist. So assume f is a continuously differentiable function at x star at the fixed conditions are there. First condition, if absolute value of the derivative evaluated at the fixed point is less than 1, if f prime of x star absolute value is less than 1, then x star is asymptotically stable. For now, you can just understand that x star is stable. Don't need to worry about asymptotically stable. That we will cover later. Just know that if derivative of the function f evaluated at the fixed point x star is less than 1 in absolute value, then the fixed point x star is stable. It should lie in between -1 and 1. Yeah, because no, you are already taking a hyperbolic fixed point. You are already taking a hyperbolic fixed point. So therefore, since you are having this is less than 1, therefore it always says that this is not equal to 1. Fixed point, isn't it? This function is for real numbers. Yes. I'm not saying x is -1 or 1. I am saying f prime of x is -1 or 1. We'll take that question later. Just keep that. I will come to you. So next we will see if f prime of x star at the fixed point, the modulus of it is less than 1, then x star is asymptotically stable. If the other way around, f prime of x star is greater than 1, then x star is unstable. It's an unstable fixed point. Now you can know if you want to point, then you can compute the derivative, take the modulus. If it is less than 1, that fixed point is stable. If it is greater than 1, it is unstable. Okay. Now we'll consider an example. Consider an example here. Okay. Consider an example. This is a function g of x equals to 1 minus lambda x square. That means there is a function xn plus 1 that is equal to g of xn. This is the recurrence map, or xn plus 1 equals to 1 minus lambda xn square. Okay. So you have this discrete 1D discrete map with you. Have this 1D discrete map with you. I want to understand. My question is compute the fixed points, and analyze their stability. I will tell you where this is defined, where this function is defined. So you can define, this is defined in, say, defined on, this function is defined on -1 and 1. Okay, and parameter lambda is a parameter lambda can be in this range 0 to 2. Now can you find the fixed point of this map? So to find, let me answer the solution. Okay, so to compute the fixed points, we don't know if it is a fixed point or a fixed points. Okay, is there exist one fixed point or more than one? We don't know. So fixed points of xn plus 1 equals to 1 minus lambda xn square is given by star such that it has to satisfy x star equals to 1 minus lambda x star square. Now, can you help me with this in computing x star? Can you tell me what is x star from here, from the quadratic equation? Please do the calculation and let me know. Fine. That is, say x1 star will be like minus 1 minus root over 1 plus 4 lambda divided by 2 lambda, right? Yes. Everyone okay with this? And x2 star minus 1 plus root over 1 plus 4 lambda divided by 2 lambda. Okay, these are the two fixed points. Now we want to understand which one is stable and which one is unstable. Okay, how you will compute it? So what is f prime of x star? What is sorry, g prime of x star? You have to compute this to find stability, right? So what is g prime of x star? First of all, what is g prime of x? G prime of x is minus 2 lambda x. Is it okay? Yes, with you. Is it okay with it? Okay with you? Why we are getting it? Maybe for bio people it might be sudden. Show the step. You can show the step. So g prime of x is minus 2 lambda x. Okay. Everyone is on the same page. Now, for x1 star, for x1 star, for x1 star, we want to evaluate what is g prime of x1 star. That is equals to mod of minus 2. You see the value here, lambda into x1 star. X1 star is given by this quantity over here. That is minus 1 minus 1. Yeah. I'm with you, right? You can cancel out this. So we will have minus of, actually plus 1 plus, isn't it? Yes. From this, now you have this inequality 1 plus 1 plus 4 lambda is less than 1. That means this quantity lies in between minus 1 and 1. This is a well-known fact. Okay. With you. Solve this inequality. Solve this inequality. Like, I would ask you, what we are doing is actually correct, or we are just solving it? Please see, don't think of this as just equation. See each and every element of your calculation. The thing we are doing, is it making sense? There is no. Why it doesn't make sense? Okay, I will ask you to observe this quantity alone. This quantity is 1 plus something, a positive quantity, and you are asking that quantity to be less than 1. That is never true. Okay, so this cannot happen. Not true. So that means what you conclude, therefore 1 plus will always be greater than 1. It can be equal to 1, but we are considering greater than 1 for now. The only possibility is it is greater than 1. Okay, it cannot be equal to 1 also. So therefore, what you conclude, this implies that x1 star is unstable fixed point. sense with this? Prime of x1 star. And this quantity is coming to be greater than 1. Okay. And according to our previous definition, if the derivative is greater than 1, it is unstable. From part B, so therefore this is unstable. Okay. Now my next question is, or maybe we'll do it here, is actually to find about x2 star. What about, to tell me the stability of x2 star? So for that we will evaluate g prime at x2 star. And that quantity is given by -2 lambda times -1 plus 1 plus 4 lambda divided by 2 lambda. Yes. So this is equals to 1 minus this quantity. Now you will have, this will give you a range of lambda, where this will give you a range of lambda. Is to find this range. Okay. Solve this inequality and find lambda belongs to which range. Lambda belongs to what? Okay. This parameter regime will tell you that x2 star is stable for this value of range of lambda. Okay with you? Everyone on the same page? Same page, isn't it? Got it. Any issues? Any queries? Let me know if you don't understand. Once more, you have this equation, right? Xn plus 1 is g of xn. This is your iteration equation. I want to know, compute the fixed point of this map, discrete map, and compute their stability. Which fixed point is stable, which is unstable. What I do, in order to compute the fixed point, you have to do x star equals to g of x star. That's what I did here. Fixed point is given by x star such that x star is equal to lambda x star square. From there, using quadratic equation, you got these two roots, x1 star and x2 star. Okay. Now, in order to find which fixed point is stable, you have to compute the derivative. That is, and you got the derivative of g as -2 lambda x. Okay. Now, the only step remains is to get this derivative at the fixed point to find the stability. So you have to evaluate this g prime x at x1 star and x2 star separately. First, I am doing for x1 star. For x1 star, g prime of x1 star is given by this quantity. This quantity can never be less than 1 because it is 1 plus a root over of a positive quantity. So therefore, it is never less than 1. Fine. So only possible case is this is greater than 1. If it is greater than 1, by definition of the second one, it is unstable. So therefore, this x1 star fixed point is an unstable fixed point. Okay. So stability of x1 star is known. Now you have to compute stability of x2 star. Evaluate g prime at x2 star. So you got this inequality. Now this is possible because 1 minus a positive quantity can be less than 1. You have to find for what lambda this is true. Solve this inequality. This is your homework. Solve which lambda. Lambda belongs to what range that satisfies this equation. And in that parameter range only, fixed point x2 star is stable. Only for this parameter value lambda, fixed point x2 star is stable. Outside this parameter range, it will be unstable. I welcome you to try this map here, cobweb diagram, and see it in person that this is true. The calculation just you did. Okay. All right. Now, okay. Now let us move discussed concept in many courses in nonlinear dynamics. Okay? Many don't cover this concept. Many know the concept till now that if you less than 1 it is stable, greater than 1 is unstable. But what if your derivative is equal to 1? If your derivative is equal to 1, from the very definition of hyperbolic fixed point, it violates the hyperbolicity. That means if um, if f prime at x star is equal to x star is a non-hyperbolic fixed point, that we know, right? But our previous theorem only told us the stability criteria if f prime is less than or greater than 1. So how, if in your map, how will you know it is stable or not? You have to develop new theories. Okay. So this is where the calculation gets a bit more complicated. Most importantly, maybe it will not be important to you. This is the bit complicated part, okay? But I will just talk to you, and it's fine if you don't understand also. Okay? But try to understand this. Okay? It's all the concept will be based on derivative, nothing. Fine. All right. So in this kind of situation, how to find stability? How to determine stability in these cases? Huh? Actually, I'm not able to hear you. Can you huh? Yes, derivative is like slope, and yes, you can think of the same as here. You can think of like the same as here. Why this point is stable? Can you draw the slope here? Okay. Yeah, if you include theta and all those things, it will just get complicated. But if you have the function, you just for the slope. Why you go to finding angle and then take 10 feet? Can be there. Okay. How to determine stability for this case? That means for a non-hyperbolic fixed point, how you will determine stability? So this will lead to two cases. We will consider the case of f prime x star minus 1 and f prime x star plus 1 separately. We have to do it separately. There doesn't exist a single theory which can cover this. Okay. Okay. Let us consider the case of f prime at x star equal to 1. Okay. Let us consider this case. So this is a theorem. Let x star be a fixed point of the map. X star be a fixed point of f, the map f. Okay. Such that f prime at x star is equal to plus 1. Okay. That means we are non-hyperbolic regime we are in. And also you are assuming that the further derivatives of f are continuously differentiable. Okay. That means, and assume that f prime at x, f double prime at x, triple prime, okay, 3 times derivative are also continuous at x star. Then the following statement hold. Then following statement hold. Part A, if since your first derivative is not giving you any information, the best logic is to get help from the second derivative. Okay. Now the list of statements will involve stability based on the second derivative. Okay. So if f double prime of x star is not equal to 0, then that implies x star is unstable. Okay. Part B, if f double prime of x star is equal to 0 and f double prime of x star is equal to 0, that means f double prime is also not giving you any information, then you take help of the third derivative. So that is f triple prime of x star. If it is greater than 0, x star is still unstable. Case 3, if f double prime x star is equal to 0 and you have to take the help of third derivative, what can be the sign? Less than 0, isn't it? Because you consider greater than 0 in the second case. If the third derivative is less than 0, then yes, x star is stable. Okay. One good example I would like to say in this, it might appear a bit mathematically complicated. One good example I would like to say is consider this 1D discrete map in action. What is the f of x here? F of x is minus x cube plus 1, isn't it? Yes. Sorry, no, minus x cube plus x. Following the idea, right? Yes. So I want to understand the stability of the fixed point. Now x star is a fixed point of the map. How many of you say it is false? Is it true? Do you think? Yes, x equal to 0 is a fixed point. Because why? X star equal to f of x star. That means x equals to minus x cube plus x. Sorry, x star, x star. What is the root of this? X will be cancelled with x. X cube equal to 0. But it cancels, no? So you are left with 0, isn't it? So x cube equal to 0. X cube equal to 0 meaning x equal to 0, isn't it? So x star is a fixed point of the map F. Okay. Now I want to analyze, is this fixed point stable or unstable? So from your previous theory, what you do? Take the derivative of the map F. What is f of x equals to minus x cube plus x. Now I am asking you, what is df by dx? That is f prime of x. That is equals to minus 3x square plus 1. Isn't it? Fine. Now I am asking you, at x equals to 0, which is the fixed point, what is f prime of x? X equal to 0 here. What you are getting? So f prime of x star is equal to minus 3 into 0 square plus 1. That is 1. So your first theorem fails. Your first theorem here fails because it is only you can find if it is less than or greater than 1. Okay, you can't use this anymore because it is less than or greater than 1. So what you can use? You have to use this one where f prime is x equal to plus 1. Okay. Now first derivative is not giving you any information. So you go to second derivative. Can you tell me what is the second derivative of f? Second derivative of f double prime x minus 6x. Yes. Now, what is f double prime of x? So at x star equal to 0, what is the value of f double prime at x star? 0. So it is not giving you any information. Which one you should apply? So this case is failed. This part A is failed. Okay. So either part B or part C can happen. Okay. So what you do? You go to the third derivative. What is third derivative here? d3f by dx3 minus 3. Sorry, minus 6. What does it mean? So f prime at x star equals to 0, triple prime of x star equals to mod of minus 6, that is equals to 6, that is greater than 0. Oh, sorry, no, we don't need to consider mod, right? Sorry. At x star equals to 0, what is f triple prime of x star? Minus 6. It is less than 0. So out of B and C, which one will be applied? Out of B and C, which one will be applied? C, because here f prime, f triple prime. Okay, follow my cursor. So what you consider here? X star is stable. Yes. So what you conclude from here? Yes. So x star equals to 0 is stable. I invite you to check this concept again by utilizing the cobweb diagram and let me know in the next class. Wait. So I will please give me figures for this. Store the figures. Okay, I will ask randomly anyone in the next class to give me the cobweb diagram for this x star equal to 0. Okay. All right. Wait, we are in a flow, so I'll just come to you. I'll come to you. Okay. So you got an idea for this? So see, this example is for the case when f prime at x star equals to 1. When f prime of x star is equal to 1. Theorem. Okay. Now, there can be another case, right? Where f prime of x is minus 1. Now this case is remaining. Now this case is remaining, isn't it? So we have to deal it separately. Another case. Okay. So just go with me. Just go with the flow. Don't get stuck in between. Just go with me in the flow. Okay. So next we will consider. So next case. Okay. When f prime at x star is equals to minus 1. Okay. Yes, you need to consider a different type of derivative, which I think you might not have heard of. That is known as Swarzschian derivative. Okay. It's not Sejuan's. It's Swarzschian derivative. Okay. Swarzschian. Okay. So let me write it here. I have the accurate. Okay. So it's denoted by SF. Okay. SF. It's good for you to know this, and for a particular function, for a function f, SF is given by SF. Of course, it will be a function of x because we are taking a derivative. It is given by this huge quantity. Yeah. No need to worry about this. I told you this part will be technically involved. It's okay if you don't get it. Okay, but you should know about this. So Swarzschian derivative is given by this function. Okay. So can you tell me if we adapt our Swarzschian derivative to our case, that is if f prime of x star equal to minus 1 case, then what is SF of x star? Just put f prime of x equal to minus 1 in this equation. So you will get minus double prime of x star and square. Are you on the same page with me? I just substituted f prime of x to be minus 1. Nothing else. So now the theorem states if the Swarzschian derivative at x star is less than 0, then it implies x star is asymptotically stable, or stable you can say for now. Okay. Second case, if Swarzschian derivative is greater than 0, then x star is unstable. I'd like to consider one example here for you. Same as we did in the last class, sorry, in the previous page. Take this example, xn plus 1 is equals to xn square plus 3xn. This is your iterative map. Iterative map. And this is f of xn. So what is f of x here? F of x is x square plus 3x. And I am saying, say it is defined. This function is defined on minus 3, 3. Just for clarity. Okay. So I am saying compute fixed points and their stability. Compute fixed points and their stability. Okay. How can you compute the fixed point? So fixed point is given by x star square plus 3x star equals to x star. Isn't it? Can you give me the root for this? What root satisfies x star equals to? Please see carefully. Please see carefully. Root 2 won't come. Yeah. So check that one will be 0 and another fixed point will be minus 2. Okay with you? Yes. Now we have to find what is the stability here. Okay. For x1 star, for let us see the stability of x1 star. What you do? Compute the derivative at x1 star. What the derivative is? F of x is this. So df by dx is x square of d by dx of x square is 2x, isn't it? Plus 3x. Derivative of 3x is 3. Fine. So 2x1 star plus 3. What is x1 star? 0. So this is mod 3. Sorry, I should not have taken the mod. You should tell me. I should not have taken the mod, no? It's just the value. It's just the value. What is this? 0 plus 3, right? This is greater than 1. That means it is unstable. How it is unstable? Depending on this one. F prime of x is greater than 1, it is unstable. Now the trick part lies for x2 star. x2 star. For x2 star. For x2 star, what is f prime? What is f prime? What is f prime? Minus 2. It is 2 into minus 2 plus 3. Minus 1, isn't it? Minus 1. So you have to apply this case. You have to apply this case. So Schwarzian derivative we have to evaluate. So can you evaluate that quantity for me? SF of 2, SF of minus 2. So you have to find SF of minus 2. So implies SF of minus 2 decides the stability. What is SF of minus 2? Can you compute from this quantity here? Value. SF of minus 2 equal to what? Please do it now. Okay. Okay. So take this fixed point into action. This is the fixed point. Okay, this is the fixed point. Now I want you to take this condition. The first part A. The part A, f prime of x is 1, f double prime is greater than 0. And the follows that case. You don't need to worry. You can check because the function is concave upwards. In part B, you can see it is downwards, concave downwards. Okay. So if you see this point, I am taking two initial conditions. Please see it carefully. One initial condition is this, another initial condition. The cobweb is going out terms. That is diverging. That it is diverging. But if you take the fixed point on the other side of the fixed point, that is this case, then it is kind of converging. So it is converging on one side and diverging on the other side. Still it is stable, but it is known to be semi-stable. Semi. That is one part is stable, one part is not. So I want you to show how the dynamics, how complicated the dynamics can be. Always it is not the case what Mr. Sangamesh was asking to take negative x naught and see where it is going. Luckily, it went outside. But if it was this case, then yes, it would have been converging to the fixed. Okay. So I told you to wait for this idea. Now the next idea you can see when it is less than 0, f double prime is less than 0. This is part B when f double prime is less than 0, and you can see this is the curve f of x, and it is concave downwards. It is facing downwards. It is facing downwards, isn't it? Here, see here it is facing upwards. Here it is facing downwards. Both of the cases, you can take any initial point, it is diverging, right? Yeah, here it is converging. It is diverging this side, but converging this side. So again, it is semi-stable. Semi-stable from the right. Okay. Part C is f prime is 1, f double prime is 0. Both of the cases failed. You have to look into the third derivative, which looks like this. Okay. And you can see since the third derivative is getting so any initial condition is moving away. All right. So it's an unstable fixed. Part D, f triple prime is less than 0, and you can see both of the initial conditions are converging. And these are pretty hard systems to analyze because finding the fixed point is very hard here because y equals to x and y equals to f of x are very close to each other. Okay. So these are like singular kind of systems. So you have to be very careful in this kind of systems. Anyway, we just showed you graphically how these cases can occur. And now, another case. So recapitulating your previous class, now you can see why this fixed point is stable. So if this fixed point is stable, of course, in logistic map, the derivative evaluated at that fixed point is less than 1. It must be. Okay, therefore it is stable, you can see. Then it bifurcates to a period 2 orbit. A period 2 orbit you are seeing. Okay. Then a period 4, period and so on, then chaos. Chaotic orbit. Right? Now you understood so far how to find the stability of a fixed point. Now I ask you how you find stability of a periodic. Now we are stepping one step up. Stability of fixed point is done. Now how you can tell that stable period 2 orbit is stable, or period 4 orbit is stable. Stability of periodic point. This is a very nice concept. Stability of periodic point totally, hugely depends on computing the stability of fixed point. How? Yeah, that's the catch. And that's where I'm coming to. Okay. So next part of the lecture is on the periodic points. Periodic point. What is a periodic point? Last class, you saw the time series of the logistic map, and you told me that from the time series, what is the period of that periodic orbit? By looking into a point and checking after how many iterations it is again repeating the same point. Okay, that is a periodic orbit. Okay, now we will formally define what is a periodic orbit. Okay. What is a periodic orbit? I will recapitulate. Like I will make you remember once again. You start from x naught, iterate your map f, go to f of x naught. This is x1. Next point. Iterate your map again, go to x2. That is f of x naught or f of x1. Fine. Okay. Suppose now after iterating, you are again going back to x naught. Then what is the period of this? 3. Why? Because f3 of x naught is again x naught, isn't it? So now we will generalize this idea. Basically generalize this idea. Okay. So okay, let us start. But if you see, all of these points are periodic points. So this is a period 3 orbit. This is a orbit. And what are the elements of that orbit? Suppose A, then B, then C. Then elements of the three orbit are A, B, C, or x naught, f of x naught, f2 of x naught. If you say, sir, how about I add f3 of x naught? Then you know f3 of x naught is again x naught. So therefore, we don't need to write it. Okay. So there is no need to write that in the set. So this orbit, period 3 orbit, is composed of these 3 points. Are you getting the concept clear? Okay. Now we will generalize this concept a bit mathematically. How fixed point, how the stability of periodic point can be understood from the perspective of stability of fixed point. Okay. Let me write this. Now here we reserve x star for fixed point. Here we will use x bar for periodic point. Just the change of notation, nothing else. Okay. X bar is said to be a periodic point period of, say, period k. So periodic point of map f, okay, with period k, okay, if f composed k times at x bar is returning to the same x bar, isn't it? Yeah, something like that. So f3 of x naught is again x naught. So if it is a period k point, kth iterate of f at x bar will so this kind of point for some I did not say what is k, for some positive integer k. Okay. And with you so far. Now see, something very nice is happening. Can someone sense some? Have you seen this one before? Have you seen this one before? How about fk times is again a function, isn't it? F, what is this one mean? This means f composed with f, again composed with f k times. This again is a function. This again is suppose I say this is g, function g. Okay, suppose this is function g, then what you write? G of x bar equals to x bar. Now can you let me know, is this reminding you of something? This is saying that this is implying that x bar is a fixed point of g. isn't it? Now what is G? G is f of k. Fine. So therefore, like you can see, like it is like a periodic point x bar, which is a period k point, most important. Okay, x bar, which is a period k point, is a fixed point of fk because k of x bar is equal to x bar. That's what we should do next. Okay. So now you got the idea. Now you got the idea how stability of a periodic point can be boiled down to understanding stability of a fixed point, but not of the same map, but composed map. Got the idea? Yes? How many of you did not understand? Okay. So what I am saying is this one you got it, this function here, fk of x bar equal to x bar. That is a definition of periodic point. Okay. Now I am asking you, fk means f composed with fk times. That is again another function. Let me. So what it means? G of x bar equals to x bar. Have you seen this quantity before? This is a fixed point. This says x bar is a fixed point of function g. Now what is g? G is f of k. So x bar is a fixed point of f of k. Okay. But what is x bar? X bar is one of the periodic points. Okay. But it acts like a fixed point of the composed map. It is an analogy. It is an analogy. Okay. So x bar, which is a period k point, is a fixed point of fk, not f. It's not a fixed point of f. It's a fixed point of f composed with fk types. Okay. Now, as one of you pointed out, after this, how can we determine the stability of this periodic point? Again, the same concept, all boiled down to derivative. Okay. Now we ask when a fixed point is stable. Sorry, when a periodic point is stable. First condition, x bar is stable if stable if it is a stable fixed point of fk, isn't it? That's how we use the analogy. Okay. Now, how can you see this? That means you have to compute fkth derivative, right? Fkth derivative. Fkth derivative at x star, that should be less than 1. Isn't it? How you will get this? How you will get this? Tell me. Any ideas? You can use chain rule. You can use chain rule. You are taking the derivative d by dx of this quantity, right? D by dx of this is less than 1. You can use the chain rule. Okay. Using chain rule, convince yourself that, let me write it down, it's in my note anyway. So f prime of x1 bar, f prime of f of x2 bar, so on. Okay. X1, x2, all these are periodic points till xk. Okay. Same till f prime of xk minus 1 xk. This is less than 1. Okay. So here the chain rule is there. Chain rule. Okay. So please try to understand how this works. Okay, this is a bit complicated. We won't go into detail. Okay, but you know this, that there is a concept like this, like you apply the chain rule. Unstable otherwise. If it is unstable, this quantity should be greater than 1. Fine. So now at least now at least you know how to compute stability of a fixed point, how to compute stability of periodic point, how to boil down stability of periodic point in terms of stability of fixed point. Okay. We will do some calculations in upcoming classes based on logistic map. So in the upcoming class, what we will do is we will actually compute the fixed point here and the period to orbit here for logistic map. Now that you know how to compute fixed point, how to compute periodic. Fine. So yeah.